Good afternoon, everyone. Oh, I see Mark's just joined. That's great. Good afternoon, everyone. Thank you for joining us today for this virtual seminar under this ESA's Roundtable Systems Seminar Program. It's my great pleasure to introduce our distinguished speaker today. It's Dr. Gavin Hess. As you can see from the background of his Zoom or from the slide here, there are a lot of solar panels, right? And that's exactly his expertise and an area that I did kind of a little bit intersection with him. So Dr. Hess is a distinguished member of the research staff at the National Renewable Energy Lab at NIERO. He's well known for his area of research in terms of analysis of environmental impacts of energy systems. That covers a variety of topics, ranging from shale gas nowadays to solar panels. I think the first few papers I read from Gavin was really about his earlier work, pioneer work in this area of shale gas, right? And recently he became a very active and well known in the field of solar panels as well. So he received his bachelor's degree from environmental science in Brown University and then MS and PhD from UC Berkeley. He leads the International Energy Agency's Photovoltaic Power Systems Technology Collaboration Program. That's Task 12 on sustainability. And he's quite well known in general in areas of sustainability, life cycle assessment, publishing a lot of top profile papers in Science, Nature, PNAS, and relevant journals. So it's really a pleasure to have him here today. Please join me to welcome Dr. Gavin Hess to our seminar program, and let's look forward to his presentation about sustainability of PV for the terawatt era.
Great, thank you so much. I apologize for not being there in person. I really would like to have been, but I think as I've heard many of your other seminar speakers have had to do this remotely. I hope there'll be opportunities to meet some of you in person at some point in the near future when we all can travel again. But in the meantime, we have a job to do to try to decarbonize our economy, and photovoltaics is going to be it seems going to be one of the primary mechanisms for us to do that. With that scale up, there arise a lot of questions about the sustainability of this technology, which does very clearly offer decarbonization potential, but also can present some challenges which the National Renewable Energy Laboratory, where I work, works on behalf of the Department of Energy and other funders, as well as international work that I do leading this task that's focused on sustainability of PV. So an outline of the talk that I am prepared today, I wanted to kind of take us through where we've come in terms of prior research, focusing on sustainability of photovoltaics. First, it started with sort of the incremental addition of photovoltaics when it was very, very, very small portion of our electricity generation system. We really only needed to think about the increments, small increments of additions of PV. So they're isolated systems and they're considered in a static manner. We learned a lot. And then that progressed to sustainability assessments that are still, I think, a little more at the cutting edge, thinking about PV and systems, doing dynamic approaches to analysis of photovoltaics within these systems. This is what we should be doing now. But PV is going to expand, and I'm going to show you some highlights from a very recent study that was published by the Department of Energy, but that NREL really led in the development of. It's called the Solar Future Study. And it starts to consider PV at this multi-terawatt scale. And we then can ask other questions, or we should be concerned about some other questions. And we have some early answers to some of those things, but of course need further study. And then finally, to end on some future research directions, what we should be starting to do now so that we can get ahead of some of these questions and answer them. So I'm going to start with what are called process-based life cycle assessments, LCAs. I've done a lot of work in this area over the years. There's certainly continued interest in doing process-based life cycle assessments, but they allow us to make commensurate comparisons of technologies per unit of incremental addition, per kilowatt hour added to the system. The plot shown here is a review system, what we call a systematic review that I led a decade ago. That was then featured in the IPCC Special Report on Renewables, and became the central focus of a special issue of the Journal of Industrial Ecology and has since been published elsewhere. But we assessed all of these different electricity generation technologies. We systematically reviewed the literature. We have reviewed to date well over 3,000 published life cycle assessments to come to this kind of figure. And it clearly shows that on this life cycle greenhouse gas emissions gram CO2 equivalent per kilowatt hour basis, again, sort of that incremental addition of a kilowatt hour, that those electricity generation technologies that are powered by renewables, photovoltaics being one of them, has characteristic, so central tendency, life cycle GHG emissions at 50 grams CO2 equivalent or lower. Nuclear is also in that same camp, at least by these published life cycle assessments. And of course, then the fossil-based non-renewable technologies, you can see that sort of stepwise increment at benchmark 500 grams CO2 equivalent for natural gas, 750 or so for oil, 1,000 for coal. And there's pretty robust basis for saying that these are the estimates that would be relevant. And despite technology innovation and changes in technology, they've stayed pretty stable. I mean, they fluctuate somewhat, but these are sort of the rankings, and really the benchmark central estimates are pretty much current. But what this doesn't consider is they do consider the detailed accounts of the current state of technology, but they're considered in isolation, and they're not deployed at scale, nor are they where they could change markets and systems. So PV has very low greenhouse gas emissions on this basis, but the effect on incumbent generators, so how does a large scale introduction of PV affect then the operation of natural gas plants, the operation of coal plants, even the operation of hydro or others is not considered. End of life management, that's EOL, is typically not considered in these studies. It hadn't been to date. The energy supply mix, and as that changes, is not being considered in these. So there are many separate individual issues that are missing. Greenhouse gas emissions isn't the only thing that process-based life cycle assessments have considered. We also have considered water consumption, certainly a growing interest in the availability of water. And on a life cycle basis, it does miss the accounting for when and where water is available, because in life cycle assessments, you aggregate over time and space. So it gives you one measure of that total water demand, but really to be able to better understand and situate this water consumption, in this case, you need to also understand where and when. So that's another sort of deficiency of this process-based approach. But you can see here that photovoltaics is very small in comparison to many of these other technologies. We've divided the water use by the phase. So the power plant, or rather building the power plant, the construction, is almost all of where water is used for photovoltaics, so in the manufacturing phase, as opposed to its operation and for those thermal plants, then for the fuel cycle. And you can see that that by far the dominant water use for electricity generation technologies is in that operations phase, and that's because thermal plants require cooling. And cooling traditionally has used water, evaporated that water, and that counts as consumption. So even renewable technologies that are thermal-based, geothermal and concentrating solar power, will have high water use when they use water for cooling. And so the difference, probably the best way to characterize technologies for water consumption is thermal and non-thermal, rather than renewable and non-renewable. Land use is emerging as an important issue, especially with the scale up of systems. Again, on a per unit basis of here, a megawatt hour per year added. We've done empirical studies based on satellite imagery and documents about the land occupation of a range of different renewable technologies, including solar, but also wind and geothermal. And so the table here represents the average of those, the N being the count of systems that we did that empirical assessment on. And you can see in this direct area measure, the far right column, that PV is somewhat larger, but basically on the same scale as concentrating solar power, but an order of magnitude larger than geothermal or wind. Now, this can be compared to, in which it often has not been properly compared to, which is our incumbent energy technologies. So natural gas, coal, nuclear, et cetera. And this is a favorite point of comparison incommensurately, improperly, I would say, for those who make comparisons to nuclear or fossil fuels when they don't count for the area required for the fuel cycle. So where are those fuels provided and how much area is required in that provision of fuels and also the transportation of those fuels to where they're used. Often it's only compared at that for the power plant itself, which I would say is not the fair comparison. A study I helped to publish several years ago was the first one really to account for this life cycle land use in a robustly empirical way for natural gas electricity. And we found that it was 0.62 meters squared per megawatt hour, which of course you can see then is larger than for photovoltaics and any of these other renewables. And this work really has yet to be repeated for coal, for nuclear, as well as for other basins that would produce natural gas. We only looked at one, which was the Barnett, which is around Dallas, Fort Worth area in Texas. But you could imagine that perhaps land use, land occupancy along the fuel supply chain, especially in Pennsylvania for the Marcellus, might look a little bit different than around a peri-urban area in Texas. So more study needed. More recent life cycle assessments, you can see in the top right corner of the screen. Now we're at number 2 in my outline. So now we're considering advancements in our assessment of these environmental impacts of photovoltaics, and we're getting into more dynamic considerations. This was a study I was involved with, which was I think early in the evolution of these methods, where they account for a changing background energy system. So in a projection of photovoltaics going out to like 2030 or at the time, or 2050 now, should also account for the fact that if you are adding more photovoltaics to the grid, then your electricity provision and the carbon intensity, for instance, or water intensity or other metrics of the grid is changing over time. And so the next generation of photovoltaics being manufactured draws upon a lower carbon intensive or a lower changed, maybe water intensive grid. And so by evolving that background and also evolving the technology, the design of the technology. So for instance, for photovoltaics, we know that we've seen a large decrease in the thickness of the silicon wafer, or we've seen a large decrease in the amount of silver used per PV module in the mass within the PV module. We've also seen a great increase in efficiency of these modules. All of these are technology evolutions that one can attempt to account for within these life cycle assessments so that they're dynamic and consider the changes over time. So this study focused on that. The diagram on the left is sort of a picture of the method that was put together for this. And on the right, it shows some of these changes for 2 different thin film technologies as we went from the impact in 2010 and consider different factors like if we have recycling of the system, if we have efficiency gains going to 2030, dematerialization, that's the thinness of the wafers or the less silver use. If we change the background energy system, is the blue map, an IEA projection. And then finally to get to that impact in 2030. And so in this waterfall, you can see the effect, and it differs by different impact categories, the effect of these changes that you're accounting for over time. PV being considered as part of a system, many, I would say, and probably even most at this point, PV systems on utility scale are being proposed with battery storage alongside these days in the US. Also, that's being certainly very much considered in residential markets. So we've done one study, and there's a small set of studies that have done something similar of looking at PV plus battery storage. Now we're considering this system deployment where PV is not considered alone, but being considered in the change in the energy provision system, and so often co-located, sometimes not, but paired together. And of course, we know that when you have photovoltaic electricity that's in excess of what is demanded by the system at a period of time, if you don't store it, then you're wasting that energy. If you can store it, then you're able to transfer that energy from one time period to another, where it can still then provide that same decarbonization potential, et cetera. So this study looked at then some different scale size systems for a residential PV plus battery storage system. It happened to be that this case was analyzed in Switzerland by colleagues of mine that under the Photovoltaic Power Systems IEA banner. So now we're moving to part 3 of the presentation, and what are some concerns about photovoltaics at terawatt scale? So now if we've progressed to looking at these increments of kilowatt hours added at a time, but now we're looking at these larger scale impacts, it raises a whole host of other questions. How much land could PV require? What effect could PV have on human health when deployed at these scales? What could be the material demands of terawatt scale photovoltaics? This one's getting a lot of attention, especially with regard to supply chain concerns that exist today. What are the end of life implications? So if we're adding this much PV, do we have systems that can address PV at end of life? Hopefully with circular economy focused efforts, but eventually these systems do reach end of life where we have to make choices, and especially in the US where there's no mandates like Europe has. There's already a lot of landfilling going on with these photovoltaics that have reached end of life today. What effect could PV have on ecosystems and species, which of course relates to how much land, but then more specifically about where they're located and how, of course, we can mitigate any potential negative impacts. And then one additional question, and of course this list could go on, but one additional question, what effect could PV have on grid operations? And that's especially in terms of the environmental impacts. So embedding PV, not just with the other systems that they're installed with, like batteries, but within the whole network, the whole grid, and what effect it can have on these incumbent generators and the grid operations as a whole. For these, the questions that I'm highlighting in red, I'll be able to show some answers that we've come to quite recently, published in September, this Solar Future study that I mentioned at the beginning, that the Department of Energy published, but NREL did most of the research for. So we'll get to look at the answer to these questions in the context of that published study and the scales that they in particular evaluated. So to that end, I'm going to switch sort of slide formats and branding, you'll see. This comes from an overview presentation that the Department of Energy put together and that they and NREL colleagues have been presenting, just to give you an overview of the study, to understand a little bit about it, to then be able to interpret what the results are. So the purpose of this study, it really fits in a series of studies that Department of Energy's Solar Energy Technology Office has done roughly every 5 years. And the first one was the Solar Vision study. And from that, they established their Sunshot initiative, which was trying to reduce the cost of PV electricity down to $1 a watt. That was their goal. And if some of you have been following the progress of especially cost declines in PV, you'll know that on utility scale systems, we've actually hit that. And it's pretty amazing, the kind of cost reductions that we've achieved over time. So because it's been, cost reductions have come faster than most really ever expected, and the learning curves have been tremendous and been robust and consistent. They haven't died off yet. This Department of Energy continues to want to re-up their goals and visions every 5 years to keep up with the technology. So this one fits in the series. So it's meant to be a comprehensive review of the potential role of solar, that's not just PV, but also CSP, concentrating solar power, which is a thermal energy technology, in decarbonizing the grid by 2035 and the energy system by 2050. Of course, these are the Biden administration goals. So it addresses other large trends and activities across the US economy. And prior vision studies have really been much more narrowly focused on solar, But as solar increases and as we're getting concerned or making administration goals about decarbonizing the whole grid and also then the whole energy system, we have to start opening our lens to think about solar in all of these systems and not just alone. And so it builds an analytical foundation to guide the next decade of solar research that they're going to sponsor. And some of you who are following this may know that I forget how many millions of dollars are going to the solar department, but under even the infrastructure bill that's just passed and been signed this week, there's increased in research funding coming to this department within Department of Energy, and of course Department of Energy at large also. So there are many different chapters within this report. They focus on the future scenarios, they focus on technology advances, they focus on equity, another Biden administration goal, grid integration of solar, cross-sector interactions. So there's a chapter on industry, there's a chapter on transportation, there's a chapter on buildings, supply chain issues, and environmental impacts, which is the chapter that I led. So here's the deployment projections. One is the focusing just on the decarbonized grid, and the other is that whole energy system. So including electrification of the three sectors that I mentioned, electrification of buildings, electrification of industry, and electrification of transportation, that creates additional demand for electricity, which opens up the possibility for increased deployment of solar. So, but on the latter, it was a more simplified analysis. We have, to date, built models around the provision of solar to supply or decarbonize the electric grid. We do not have nearly as much analysis and models available to assess the electrification of, for instance, in particular industry, and then what implications that might have as feedback to the demand for solar technologies. And not just photovoltaics, but also the thermal solar energy, which is concentrating solar power. But as you can see, by 2050, just focusing on the grid, it's 1.6 terawatts by 2050 of total cumulative installed capacity, and then 3 terawatts if you consider the whole energy system. So doubling of that deployment. And that is, that's a huge, huge goal and growth from where you see we are today, or the 2020 figure, which is our baseline, because of course 2021 figures aren't published yet for what's been installed this year. So that's going to be an incredible challenge to get there, to meet these deployment. They're not exactly deployment goals; these are projections, but this is sort of now established as the target for this office and really the whole administration. So going then to the questions that I posed as ones that arise when one thinks about sustainability aspects of getting to that kind of deployment scale of multi-terawatts, what are the material demands? And how do those material demands relate to available supply and global markets? So this is a figure from the Solar Future study, and for some reason silver comes out quite pale, but that's how it was published. And you can see with the not filled in circles and triangles, that's the US demands. So just the US for the decarbonization scenario, that is just the electric grid scenario. The decarbonization plus electrification talks about the others, includes now the other sectors. That silver, silicon, and aluminum are, within the less than handful of percent of total global production of those materials. So the U.S. alone, it would seem, is not going to sort of throw out of balance the global supply, and that's 2020 supply. And of course, supply is dynamic and depends on demand, depends on the economics of that. We know these are cyclical industries. But it would not seem that the U.S. demand alone is going to change that global outlook. However, if you consider global decarbonization, so if you refer to some global projections for PV growth, then that picture changes a little bit. And in particular for silver, if you look at the global decarbonization scenarios, again, across sectors, not just the electric sector, Now we're talking about 40% of 2020 production of silver being consumed by just one commodity, which is photovoltaics. That's market moving. That's something that could present some constraints for other industries, some competition for this resource, driving up prices, and could have some implications for supply chain about the availability of where you have silver available, and then who's demanding it, and of course geopolitics of that. So that's an important consideration. Silicon is another one where there's potential for sort of changing of markets. Silicon, I'll add, is something that some of us I think tend to simplify what kind of demand for what does demand for silicon mean. Now, silicon is a very abundant element, as we all know, across the earth. Quartzite, high purity silicon, is not. Quartzite is what's needed for solar. So quartzite is what we need to focus on when we're talking about supply, not silicon supply as a whole. So that's something that has gotten relatively little attention, and I should say deserves more attention. And aluminum, being a much larger bulk material in terms of global production, the industries that use it and demand it, et cetera, only reaches about 5% of that global production. Of course, there's going to be increased demand in other sectors that need to be considered, but that one is far less of sort of market moving, it would seem. In the Solar Future Study in the environment chapter, we did some projections with a new model that NREL has developed called PV in the circular economy, or PV-ICE, of which there's I should have included it. There's a recent journal article that's I guess been accepted. I'm not sure it's been published. Is that if you look at the decommissioning of modules over time, they're going to catch up in terms of that, in terms of wattage, with the installations in the 2030s. And if you can recover, we don't have systems in the US to do this, but if you could recover all those materials and return them to the value chain, that could supply 20 to 40% of the virgin materials demands, or rather offset the virgin material demands by 20 to 40% of silver, silicon, and aluminum, the three materials we're focused on here. So this speaks again to the potential for circular economy to help to alleviate some of the supply chain challenges we might see in the future. Now, the flip side of that, the material demand, is of course, on that, the end of life materials. We tend to call it waste, but we shouldn't call it waste, because of course, if we do want to recover these materials from it, we shouldn't consider it waste. We should be considering it as having value, and try to use words that that reflect that. But this is Department of Energy slide, and it's really hard to find a single term yet to get away from that terminology. But anyway, I want to present that thinking to you to get you to think about it. And using that same PV-ICE model, PV in the circular economy model that NREL's developed, we looked at the end-of-life material mass. This is total sum of all materials in modules under a reference scenario, and then the decarbonization scenarios, the two of them. And these are kind of the flows. You can see, of course, the distinction then about how the end of life by 2050, they start to depart from the curves, at about 2040. But with typical useful lives of 30 years and actually getting extensions on that, then it takes a long time for us to have those modules come offline and have their embodied materials then potentially available to us to recover and reuse. But as I showed in the previous slide, this is a strategy that we can use to try to mitigate some of the demand and supply and incumbent supply chain issues. But we're not really prepared now, and we need to do more to prepare. And so, what are some of the things that, at least in this study, have been recommended? And by the way, the Department of Energy, Solar Energy Technologies Office, both has some infrastructure bill funding to start supporting some of this research, as well as some goals in another document that they have set around some of these issues. So development of low-cost recycling approaches. Recycling costs $30 a module or something now, typically, with some range around that. And this is really just anecdotal. There's no robust survey of that. And that compares to landfilling. If it's not deemed to be hazardous waste, you go to a regular sort of municipal landfill and you could dispose of a PV module for around $1. So pretty large cost difference. And without mandates, you can imagine the pressure to use the low cost option rather than the higher cost option of recycling. So even though we don't have any tracking of number or mass of modules that are going to one pathway or not, landfilling or recycling, we suspect that most is going to landfilling at this point. One challenge with getting to, there are two sides to cost of recycling. There's the cost of that process itself, and there's also the value you get from the materials that you're trying to sell back into markets. And maximizing value of those materials is one way to mitigate that net cost. So cost should be attempted to be reduced, but at the same time, we should try to be obtaining higher value from recovered materials, which is a challenge because these are new technologies that we're trying to recover materials from. We haven't yet even really characterized the impurity profile of, for instance, silicon. So it's hard then to sell it to a market that might demand certain constituents are removed or at minimal levels. And so, that's currently inhibiting getting maximum value. And then new policies and incentives for sustainable end-of-life practices are needed as well. In addition, another aspect one aspect of health, I asked the question about, what would be the impacts on human health? So within the Solar Future study, we looked at the avoided emissions within both the power sector and then also the transportation sectors from displacement of fossil fuel combustion if solar is added. So on the case of transportation, if we electrify part of a transportation fleet, that's then avoiding the emissions from gasoline or diesel fueling those vehicles currently. And solar could provide then, of course, part of that electricity. These estimates are very much order of magnitude. They are not detailed estimates using the most state-of-the-science modeling approaches to do so. So we sort of heavily caveat any kind of accuracy or precision about these estimates, and they are relative to the reference scenario over 30 years. So what's interesting about these results is that the benefits are of the same order of magnitude as the incremental direct system costs of adding solar. So around $300 billion to install solar to meet the 1.6 terawatt goals is balanced on order of magnitude basis, almost one-to-one, or really one-to-one with these benefits on the health side. So that's an important thing to consider, and you get an additional increment of another $100 billion approximately from transportation sector electrification. So, as I think some of us know, health benefits, when you monetize them, can really drive and in many cases even be larger than the climate-related social cost of carbon benefits for energy system transition. So are important things to consider on both, to have a ledger that accounts for these. Carrying on about PV and human health, there were a series of 3 reports that this International Energy Agency group that I lead has published over a series of years. These are risk assessment documents. So again, they're kind of incremental in terms of kilowatt hours of PV or so small scale systems, not large scale analyses. But they use methods from recommended by the EPA and the National Research Council, and then apply them specifically to the case of PV. So in some ways, these are really method proof documents rather than complete human health risk assessments. One aspect of that is that we only chose a single highest prioritized material in terms of toxicity to assess for each of these scenarios rather than the full set of materials. So they can't be considered a complete human health risk assessment. But we looked at cancer and non-cancer risks, and for PV that's exposed to fire, that can then lead to air emissions, and the air emissions can be inhaled, but they can also be with particles get onto the ground, they can get into the groundwater. So all these different exposure routes are considered. The second one being PV that's left in the field with broken glass. So if rainwater gets in through the broken glass, gets onto the semiconductor layer, can pull off some of the metals that then get dropped onto the surface of the earth, go into groundwater, go onto the land where they could then be stirred up with winds and get inhalation exposure. Those are the pathways assessed in the middle one. And then the final one speaks to landfills. So if you're disposing of modules in landfills, which again, we don't have empirical data understand its prevalence in the US, but we, by the cost numbers that I gave you earlier, would suspect that it's a large fraction of our modules are going to landfills. We're looking now at landfills in the third one. And I'll add that human health risk assessment methods, as recommended by the US EPA and the National Research Council, take a very conservative approach. So they're always adding factors of safety to try to assess what the potential risks are, because these methods are meant as screening levels. If you add factors of risk and you still get above a screening level, for instance, of 1 in a million increased cancer risk is an EPA threshold for cancer, then if you get above that level, that then triggers the need for doing more detailed study. So that's how these methods are meant to be used as screening assessments. And then one of the probably the most conservative assumption made for the module disposal in landfills is that they would go into unlined landfills. Those are illegal in the US. They don't exist. Now, they may exist in other countries, so that specific conservative assumption may be applicable and true in some other countries. It's not actually applicable in the US, but we took that conservative assumption just to be as conservative as possible, and again, to test if you get above screening levels. And what we found for cancer and non-cancer risk, for all three of these cases, modules exposed to fire, modules left in the field that are broken, that can lead to water infiltration, and modules crushed, put into landfills, none of them actually triggered those screening levels for cancer and non-cancer risk. So that's a good thing, I would say. And certainly on the last one, it does not mean that we are encouraging landfilling of modules. We are not. But it's good to know that if it does happen, it is not presenting a risk higher than these established screening levels. So then moving to another one, how much land will be required? This is a big question on many people's minds. And so we compare the amount of land that's used, and you saw before the increment of land. We've done empirical study on how much land PV does use. If you multiply that out by the deployment scales that we're talking about, now you can make these comparisons to other land uses in the US. So in the cumulative amount of PV and other solar, CSP2, by 2050, it's about 0.5% of US surface area. Now, of course, some states have more than others, and we looked at a per state basis in our assessment, but in the aggregate, it's 0.5% of US surface area. And you can see how that compares to certain other land uses. So urban areas and paved roadways, for instance, or agriculture, retail space in the US and golf courses. These are comparison points that one can make. I think the most interesting comparison points are to how much land is not used for a high economic productivity. So lands that are contaminated, lands that are superfunds, lands that are under the RCRA system for abatement, lands that have some sort of state level designation that's similar to the federal, those are what we call contaminated lands. And they're nearly equal in magnitude in some across the US. This is continental US, by the way, about 0.4% of US area. Some states don't have as much as others. And because some states are going to get more solar than others, it's not a perfect match. But many states have more contaminated lands than the solar that's going to be deployed in the, we project in those states. But there's another category of land, which is disturbed lands. These have degradation. So they have been overgrazed, or they have been desertification, or factors like that. And if you catalog all of those lands, that's 8% of total US land mass, as compared to 0.5% for the photovoltaics. So, multiples more of available disturbed lands than is projected to be required, even for terawatt scale. I don't know how we're going to get there, but it'd be amazing if we do kind of scales of PV and CSP. There's plenty of disturbed land available. Now, there are other factors to consider on a site-specific basis. For instance, proximity to transmission lines, land ownership issues, slope. We actually accounted for slope here, so I shouldn't have mentioned that. That need to be looked at on a case-by-case basis. And of course, there's preference for the cheapest land and flat land and land that's as close as possible to transmission. So not all of these contaminated or disturbed lands are going to meet the criteria that is ideal for the first step deployment. But there's a lot of land available, and as we go through those lands, you're going to have to move to others, and there's plenty of contaminated and disturbed available, which would then present less of that land use challenge conflict. But there's also, of course, effects on species. This is a nice study that I was not part of, but Rebecca Hernandez from University of California, Davis has done several years ago, kind of outlining all the potential effects that solar could have on the environment, and in particular, focusing on ecosystems and lands. I think that, clearly there are many different effects, but we also have to remind ourselves that we do have an incumbent energy systems and what effect do they have, including, of course, their fuel supply chains, and that there's opportunity for mitigation. And that's something that we spend a lot of time on in the Solar Futures chapter, is on how we can mitigate some of these effects on lands by, in particular, choosing lands that don't have the same conflicts with ecosystems, like with contaminated or disturbed lands. A paper I did participate on with Rebecca looked at techno-ecological synergies. So you probably can't read the chart very well, but it details a long list of all the different ways that PV can be added to landscapes or built environment infrastructure in ways that can mitigate different categories of these ecological impacts. So notable examples, and ones that you've probably heard of, are agrivoltaics, combining PV and agriculture. Even if not producing crops on lands, you can still combine PV with native species. So you're now not just grading the land and adding riprap on top and leaving it denuded, but you're actually having species that can support, for instance, pollinator habitat. You can do, an interesting one is that in the West, they have pivot rotation agriculture, or irrigation rather. So they have a center pivot and they just go like this around. And if you have a square and you have a center pivot that's going in a round circle, you have these little sections on the edges and the corners that actually could support then photovoltaics. And so there's a photo of a couple of those. And then we have, of course, PV on water, photovoltaics. So this is a really nice paper in sort of big picture outlining what are all of these different options and kind of categorizing them as far as their ability to mitigate some of the concerns that have been that are raised for photovoltaics. Now I'm moving to PV in the whole energy system. So this was a nice study done by a colleague of mine. I was not on this paper, but looking at the grid scale, but still on a life cycle basis, greenhouse gas implications of renewables and storage within the whole grid. And so it looks at this, the whole Western interconnect, so a large region, down to an hourly resolution, but over a multi-decadal horizon. So that combination of really small time step increment, but over a large span of time is a really, I think, impressive approach that they took, and looked at policies and whatever. But Life cycle results suggest that optimization models that focus on generation alone may underestimate emissions. So there is some increment of additional emissions by adding solar and other renewables in this case in large capacity over this large expanse in terms of its effect on the incumbent generators and the outlook going forward in the future that should be taken into account. Okay, now I'm getting into my last section about research directions. So these are just some amongst, I think, a much longer list, but some that I thought I could highlight. So purchase sustainable solar. This is an opportunity that we have because some solar provides an opportunity to enhance the sustainability benefits. I will be very firm in my assertion that all solar provides, for instance, decarbonization benefits. We should not be slowing down installment of solar for trying to choose one or the other, but there are opportunities to purchase more sustainable ones. And so within the EPEAT program, which is an electronics sustainability grading program that, for instance, the federal acquisition regulations require the use of for the federal government purchasing, and many states and organizations have adopted as well. There are different levels of sustainability performance that are graded. And solar, I was part of a team that developed a sustainability leadership standard for PV. It actually was focused on modules first and now expanded to inverters. So there exists a consensus-based international standard, the American National Standards Institute process was used here for classifying or grading solar for its sustainability performance. And we have an opportunity with purchasing, especially large purchasing going forward, to try to pull those from the market and expand the market for sustainable solar. Employ best practices in planning, development, and operation, as well as end-of-life management. And I provide here an example of a project that a colleague of mine leads called Inspire, innovative site preparation and impact reduction on the environment. And so this speaks to especially the native species and enhancing pollinator habitat, but also agrivoltaics. And on the right-hand side is a list of very concrete guidelines for how to employ those best practices in the development of solar that you all can refer to. And then one of my favorite topics has been circular economy. So study, create, and implement circular economy strategies. On the right is the Ellen MacArthur Foundation, which some of you may have heard of. They're by far the most prominent organization promoting circular economy. They're real thought leaders in this area. This is what's often people call the butterfly diagram. I'm not showing the left-hand side of it, which is the biological system, because it's not as relevant for PV. But on the right-hand side, you can see that the inner circles are the prioritized ones. So maintaining your systems and increasing the lifetime, going then to reuse. So maybe the first owner doesn't want it anymore. Can you redistribute it and get it into reuse? Can you refurbish or rather repair for PV modules? And maybe it has to go back to the manufacturer to do so, but then it can be maybe resold, like we get remanufactured items like computers or monitors or hard disk drives or whatever that you can purchase now. And then finally, recycling is the last one. Has gotten most of the focus, I would say, of the research attention on recycling, but it really is actually the last preferred circular economy strategy. You'd rather not get down to the elemental level, and you'd rather keep at the product level because you retain more value at the product level than you do at the elemental level. Nevertheless, there's been a lot of research on recycling, and there is a need. Eventually, all products, you can't repair and reuse them forever. They're going to reach the end of life at some point, and it would be preferable, and it's been shown in studies to be preferable to recycle rather than landfill. And so I led a study published last year in Nature Energy that provided some guidance on research and development priorities for how to advance crystalline silicon recycling technology development, and not just technology development, but also analysis, data, and modeling. But of course, we shouldn't forget that at the front end, we can also design modules for enhanced circularity. and for instance, for design for recycling. So within the IEA group that I lead, we've just published this month, maybe it was last month, some guidelines for design for recycling. So some very sort of high level guidelines about don't try to avoid adhesive surfaces. If you can avoid whole surfaces being adhered together, you have an easier time disassembling, which reduces cost and increases environmental benefits, as an example. But this is a figure that's forthcoming that we've been working on for a while. On the right-hand side in black are shown the physical flows of circular economy pathways, such as recycling, repowering, infield repair, reuse, et cetera, across the life cycle for photovoltaics. What is emerging and has received less attention are digital opportunities to enhance circularity. So one of those would be designing systems for reduced environmental impact of the materials that then go into the products, or for dematerialization. Other opportunities are platforms to digital platforms for the reuse and finding the next market for those modules. How do you identify what materials are in modules which could affect the choice of recycling system or recycling technology that one uses? Material passports, electronic bill of materials, RFID, eco-labels are all opportunities to enhance the transfer of information that the recycler would need to know that the manufacturer holds, but right now there's no information flow between those two entities. So those are examples of digital flows that I think have received much less attention, but are also important to consider. And finally, I come to environmental and energy justice. Certainly, this is a big priority of the Biden administration, something that has been studied more and more recently about solar, in particular about deployment of solar, but is something that still needs to have more attention. How can we ensure that there's an equitable distribution of these renewable energy and also energy efficiency technologies to all groups that want to participate and in decarbonization, for instance, and the energy transition, but heretofore have not had equal opportunity to do so. So the Solar Future Study actually did look at this, but in a honest acknowledgement, understands that it's not, even under these projections that we have right now, there's still not the equitable adoption. So maybe some improvement you can see between 2010 and 2018, but not much. And so a long way to go to try to get to more equitable adoption. And with that, and well, with fewer minutes than I'd hoped, but with that, those are some thoughts on PV at a terawatt scale and some sustainability impacts, but also opportunities. And I think some thoughts also about the methods that we can use as a research community to try to address some of these.
Thank you so much. This is very enlightening and very comprehensive. Thank you. I guess the floor is now open for questions. I see Mark unmute himself already. Maybe Mark, are you ready to ask any question?
Oh, I don't want to say hi to Gavin because I need to go for another meeting. Right. But I think this really comprehensive review of what's going on here. I think if I have just one quick question is that. When I see solar as part of the circular economy, I think you mentioned like a rating system for the panel, right? I suppose for the hardware or something, right?
Yeah.
But if you think of solar as a system, it's more than just a panel. So there's many other issues, right? So are there any like a development in like a more comprehensive ratings of the solar development rather than just the panel itself?
Yeah. As far as circular economy is concerned, Max, most people consider every other major component of a solar system that's installed as to be much easier to address at end of life than the panel itself. And I think there's some maybe obvious reasons for that. You know, the panel is designed for 30 years of deployment in any environmental system in the world, and it's supposed to last and perform to warranted performance for that entire time. A product that's built like that is going to be hard to take apart and hard to get at those constituent materials. Most of the rest of the balance, what people call the balance of system components, are either single elements or single materials, or some simpler, I guess you could say, combination of those. An exception to that is inverters. Inverters are electronic products that have a lot of different materials in them, but they're, so far, I think it deserves more attention, to be honest. But so far, people have considered those as, I can send them into the same e-waste management system as I do a computer or a monitor or something else, and they're going to take it apart in the same way, and they're going to recover the materials from the inverter in the same way they do already these other products. So there's been much less attention. I think that there is a need to try to understand just the mass flows, how much mass of some of these balanced materials are out there, and where are they, and when might they come to end of life. So I'm glad you raised the issue of balance of system, because I think it does need some attention.
So in addition, but also there's a mounting, there's a structure wise, right? So supporting the panel, right?
Yeah. So there's wiring, there's mounting, there's cabling, there's, I mean, if you want to carry it further, then of course there's substations and other things. But people consider those to be much easier. I mean, I've talked to recyclers, I've talked to O&M providers, I've talked to system owners. They all seem to just say, it's just not that much of an issue. Modules is where we have some trouble.
All right, thanks.
Yeah, sure.
Great. Now I see Elle raised the hand. Elle, would you like to go next? Please unmute yourself.
Yes, first of all, let me compliment you on a really exemplary presentation of a really important subject. My questions are pretty small, but one of them is, when you look at some of these things longer term, like nuclear or just other things, including wind, have people looked at, I mean, nuclear in particular has a huge, unanswered question about waste. And has anybody tried to quantify that? Because right now there's a big push to go back to nuclear. I should say a big push, an industry push, the lobbyist push to go back to small nuclear reactors. But I wondered if anybody has even an order of magnitude look at how you would consider those. And then things like wind, which I think are look very, very promising. And they have landfill problems or recycling, particularly blades. The rest of the materials in there are probably pretty easy to recycle. But is there anybody looking at that somewhere? Either of those?
Sure. Yeah. Let me take wind, because I have not studied nuclear, and I frankly haven't followed as much of that. I listened to a podcast this morning, as it happens, with Amy Myers Jaffe talking about the next generation of nuclear, looking to try to use the fuel that is rather the waste of the fuel from the first generation of nuclear. So, that would be a circular economy if that came about, and that would be beneficial, so that we don't have to mine more uranium, and we can reduce some of the hazards of that waste, but also the security concerns about that waste. But then going to wind, wind is certainly an area that we at NREL, with support from Department of Energy, have focused on. We have a number of models that we've been developing. One that's in submission is an agent-based model of all the wind power systems in the U.S. and the circular economy options and opportunities for those, focusing on wind blades, because as you're right, as you point out, Al, the rest of the wind system is, again, sort of like with solar, is a relatively simple system as far as its materials go and the management of those materials. Now, they come in pretty large mass, but a steel tower looks like a great opportunity for a metals recycler, because it may be large mass, but that's what they're looking for. They want more mass. So concrete may be another concern. rebar and concrete you can harvest. Concrete itself is going to be low value, but the blades is really where it's at. And there are recycling technologies that are being developed. Some of them are thermal pyrolysis, and there are those that would really rather not see a thermal process that would have then air emissions associated with it. But others are mechanical chemical processes to try to recover the fibers and the materials from them. So there is some attention to that, both at Department of Energy and internationally. I know that the International Energy Agency also has a kind of a sister program to the PV focused one that I'm part of, that's focused on wind. And there's attention being focused to recycling of wind blades within that International Energy Agency group.
Just, is there any very order of magnitude comparison for wind and solar that I mean, I realize you're an expert, super expert on the solar, but on the wind, is it in the ballpark as far as the other of solar? Is it look a lot better or a lot worse? Do you have any idea?
I mean, if what you're talking about, the metric you're considering is, mass or volume, those two are actually pretty different.
I was looking at overall environmental impact, basically. So an integrated view, a system view of them. In other words, is one of them clearly better, or are they kind of both? I think of them, and I may be incorrect, of course, as being very, very roughly similar in their impacts, but maybe that's not true.
Well, on a life cycle greenhouse gas emissions basis, so accounting and as best as people have in the past accounted for end of life management also, wind does have a characteristic CO2 equivalent per kilowatt hour of like 15 or so, and solar is in the 30s for crystalline silicon. For thin film, it's more like down in the 15s. So when I get asked that question, some people say, oh, well, I mean, wind is 3 times lower than solar. And I counter with, well, we're not there with our energy system yet, where the 3x difference between solar and wind matters much. What matters is the 40 or 15 compared to 1,000, and the 40 or 15 compared to 500, because that's where we're at in our energy transition. So I don't think those distinctions are ones to focus on between the two on this, life cycle greenhouse gas emissions basis.
Good, thank you.
Yeah, sure.
All right, Norm, please. Nice to see you here.
Thank you, Fen-Chi. A quick question, and to some extent you addressed it, at least with some neat photographs there of agrivoltaics.
Right.
But I was kind of curious to what extent you may have gone further into analyzing some of the potential opportunities with the agrivoltaics.
Sure. You will find some more discussion of that in the Solar Future study. So, and of course, also the paper that I actually presented the chart from, which was this techno-ecological synergies. I mean, its job was to look, pretty broadly, as also Solar Futures was, but each of them does review some of the findings of that. I mean, these are newer systems. They haven't been studied longitudinally for many years. So we don't have, the 10, 20 year empirical data about effect on, insect species or soil health or, other things. But at least from the short period of time and the few studies that are available, these look like systems that, while you want to choose your agricultural crops properly, by ones that can tolerate some shading, and you can have the proper access for harvesting by the design of how far apart your rows of PV modules are and height of PV modules in addition. Factors like that are certainly considerations that you need to optimize, but they show great promise, it seems to me. Europe has certainly been quite interested in this, and I know France in particular has had a bunch of agrivoltaic systems installed and some studies happening, in addition, I believe, to Italy. But there's this Inspire project that a colleague of mine, Jordan Machnick, leads. It has university partners across the US and some actually around the world, where they're trying to use similar protocols. So establishing similar protocols so that when those protocols that are the same can be applied in multiple locations, now you have a much more robust collective understanding about how these systems can, affect productivity of the land in terms of the harvest from it, and also, of course, the power generation. And then I think some of them are also looking at the effect on other species and such, soil health and other factors.
Yeah.
So the information is growing, and you might look at the website for that Inspire project if that's something of interest. And I think they're open to adding more university partners for furthering this research.
Thank you.
Yeah.
Great. Any other question from the audience? I have quite a few questions actually, but I don't know if we have enough time for that. So, in the interest of time, just since we still have audience, can I ask like two very quick questions?
Sure, yeah, please.
The first one is, I think, we talk about greenhouse gas emissions, and I think also mentioned land use change, also water footprint and so on. But then if you look at different kind of solar technologies, right, let's say silicon versus thin film, they are quite different, where silicon is of course more energy intensive to make, but it doesn't involve that much heavy metals, for instance.
Right.
But if you think about thin film, like cadmium, tellurium, they involve quite a bit of like, I won't say toxic, but heavy metals. And the mining process, really lead to a lot of environmental impacts. That's really beyond, I would say, land use, beyond water, beyond carbon footprint. So what's your perspective in terms of these aggregated environmental impacts? Up now it's very controversial and a lot of people are debating on that, right? But what's your perspective in terms of these, right? Because right now public really focus on carbon footprint, and which is good, but it's not everything, I would say, from LCA perspective.
Sure, yeah. I know a lot about cadmium telluride, and I know less about SIGs and other thin film technologies. But of course, their market share is so significantly less that maybe there's some excuse for not focusing on them as much. Cadmium telluride, I think, as you know, but just to make sure the audience does, there's basically one manufacturer. And it's a US company. It's the largest US manufacturer, and it's called First Solar. Having cadmium in the name of your technology does not help you in the public perception about its sustainability. So they had to work really hard, and have over a decade or more, in ensuring that there's a closed loop on cadmium. So they were the first, and for a long time, the only company offering take back of their products built into the price of the purchase of that product. Actually, they now separated those two. So now they sell products without take back, and you have an option to buy in advance take back and recycling of the product. You don't have to, but that was under market pressure. But for a long time, they built that out. It's very interesting to think about a company, a manufacturer, and by the way, there's not a supply chain as much on cadmium telluride as there is for silicon, because it's basically one company with one step in a process of putting the semiconductor layer on the backsheet. And so you don't have the multiple companies as you do in silicon in the supply chain producing different stages of that silicon and that specialize in that and do it at large scale. So they also have under one roof the recycling system. That's its own business unit. And being vertically integrated in manufacturing and end-of-life management gives the opportunity for a different perspective on how important end-of-life management becomes to the company. And so, for instance, every new module design has to have sign-off from the recycling department. Now that's pretty. I mean, it's natural perhaps from the perspective of that company, but it's pretty different than any other. And most of our linear economy, of course, is not organized around a company also taking back its same product and having to consider what's happening at end of life and how well their recycling system can handle a new product design at the front end before it's even introduced to the market. So that's an interesting thing. Second is that tellurium, of course, is a critical material. And so they need to be very concerned about the product supply. How are they going to maintain the supply, especially with growth, for obtaining that tellurium at, of course, the prices and quality that they need. With the vertical integration with end-of-life management within the company boundary, they can then think of how they can return to their own supply chain and help to secure and make more reliable their own supply chain by that recovery of the tellurium at the end of life. And they do that. Now, they don't do that under one roof. They separate cadmium tellurium into a slurry. They actually give it to their tellurium supplier as something a little bit better than, raw mineral tellurium, but it's something that company then has to develop a process to get back into the same quality that they want at the front end of the manufacturing process. So it does go out of the boundary at one point, comes back into the boundary after that processing is done. But nevertheless, that's a more circular, thinking from the beginning. Cadmium has not been eliminated, and cadmium is a toxic. I'll say it. It is a toxic material. It's a heavy metal that has significant environmental hazard associated with it, and there are many world regions that would sort of prefer to categorically say no cadmium in our products. We don't want it. But they've made an exception. Europe, in fact, has made an exception for photovoltaic modules when it can be shown that there's a closed loop, when it can be shown that there's control of that substance throughout its life cycle, cradle to cradle, not cradle to grave. And First Solar has demonstrated it. It's very, in all those aspects, I think you can see that it's quite different than the organization of the market, the organization of these companies, the regulation, the regulatory aspects, and just the product, product material management structure for a cadmium telluride in particular versus crystalline silicon.
Great. Thank you very much. Maybe just a very, very quick follow-up question. I don't want to take everybody too much time. So if you look at this technology development, right, especially for battery technologies, the batteries we used 20 years ago is quite different from the batteries that we are using right now, and we are going to develop extended 20 years. Silicon PV has been around for 2, 3, 4, 5 decades already. They have been very durable. But do you expect by 2015, as we are talking about this projection by 2015 for decarbonization or so on, do you expect we're still using this silicon PV by that time, or do you think this, thin film technologies or even something else, like organic photovoltaics or even perovskite, could play some roles in that kind of future market?
Well, my area of research and specialty is not really on markets and that kind of technology prognostication. So I don't know that I really, would be one to tell you where to bet or on this, but I can tell you that there's certainly a lot of interest within NREL and supported by Department of Energy in advancing perovskites. And perovskites, because you paint them on any surface, tandem perovskites on silicon is, one of the primary, I would say, production or design sort of vehicles for the perovskites. So silicon from that perspective, even if technology advances, to perovskite technology, it wouldn't actually abandon silicon. You'd still incorporate silicon. I think these tandem cells certainly are shown to have, that next efficiency bump that people are looking for to continue on that upward trajectory of efficiency that the NREL chart is famous for plotting over time. And yet the power of incumbency and the powers of economies of scale are such that you can't discount silicon just as a monosilicon on its own as continuing for several more decades. It's not as if they've exhausted, or it seemed to anyway at this point, have exhausted their cost reductions. And it's not as if that they've exhausted their improvement in efficiency either. So there are still technology advances, and because of their incumbency and their economies of scale, I think they're going to remain in the market for, well, I would say, at least a decade or two. But again, I'm not a technology prognosticator, so it's hard. I shouldn't be quoted on. betting on
Right.
that.
So thank you so much again, Gavin, for a very nice presentation and for joining us today. Really appreciate your time. Thank you so much.
You're very welcome. It was nice to be here.
Yeah.